So hello everyone. For better understanding of the second law of thermodynamics, we are considering this numerical. So we know that first law of thermodynamics talks about the quality of energy, whereas the second law of thermodynamics is about the quality of energy, that how energy quality degrades when it is transferred from a higher temperature to a lower temperature. And that is basically leads into the entropy generation. So we are undertaking this numerical. So let us discuss this. So we have been given a 50 kg iron block and it is at a 500 Kelvin temperature. Now this iron block when thrown into this lake, so this is a lake and it is maintained at a temperature of 285 Kelvin. So ultimately this iron block reaches the equilibrium and the final temperature of this block also becomes the 285 Kelvin over a period of time. We have been given the average specific heat of the block as 0.45 kilojoule per kg Kelvin. So we have to find out the entropy change of the iron block, the entropy change of the lake water, and the entropy generated during the process. So this problem is a basic problem in the second law, and from this we can understand that how considering the one isolated system which consists of a system and surrounding can be used to calculate the entropy generation. So we have given data. Mass of block as 50 kg. T1 is equals to 500 Kelvin and T2 which is the final temperature once it reaches to the equilibrium with lake is 285 Kelvin and temperature of lake or T infinity is also 285 Kelvin. So it is a lake is a sink, therefore there will not be a negligible there will be a negligible change in the temperature of lake. Therefore we know the relation TDS is equals to Tu plus PdV. However, here specific volume will remain constant since it is a solid. Therefore, TdS is equals to du, which also we can write as C average into dt. Therefore, ds is equals to C average dt by t. Therefore, entropy change delta S for the iron casting will be C average log of T final divided by T initial. We have been given the value of C average as 0.45 log of T final we have 285 divided by 500. Therefore, change in entropy of the iron casting will be equal to, after calculating this, as the minus 12.65 kilojoule per Kelvin. Now, since the iron block reaches into final equilibrium with the lake, therefore Q out. So how much heat is rejected by the iron casting to the lake during the heat transfer? So we can calculate this as Q out to the lake is equals to given by MC average. We are considering the average specifically for the iron casting into this is T1 minus T2. Therefore, 50 into 0.45 into 500 minus 285. So this is equals to 4838 kilojoule. Since this Q out is going into the lake, therefore change in entropy of the lake we can calculate as Q out to lake from the block divided by T interface temperature between the lake and block. So this is 4838 divided by 285. Therefore, this will come as 16.97 kilojoule per Kelvin. So we have identified the number A and number B. Now coming to the number C part. Since we know that delta S for an isolated system can be given by delta S1 plus delta S2 plus all subsystems included within the system. Therefore, if we consider this lake plus block as an isolated system together, therefore delta S generated will be given by delta S lake plus delta S of block. This also we can understand that if we have to calculate delta S of a system, then it will be given by 1 to 2 dq by t, this for reversible, plus S generated during the process. So considering this an isolated system, for lake plus surrounding, dq by t will become 0. Therefore, S generated will be given by delta S system, and if system is into two parts, that is lake plus block, then this will be given by S generated as delta summation of change in entropy of lake plus change in entropy of the block. Therefore, delta S generated during the process will be given as minus 12.65 plus 16.97. So this will be 4.32 kilojoule per Kelvin. So this is the delta S generated, and for any process to happen as per the second law of thermodynamics, delta S generated should be greater or equal to 0. It will be equal to 0 for an internally reversible process, and it will be greater or equal to 0, greater than 0 if the process is irreversible. So this was the basic numerical to understand the basic concepts of entropy generation through a basic example. So further we'll solve some more numericals based on the flow process and entropy generation. Thank you.